I'm sure we've all heard that the Earth is about 70% water, so have you ever wondered why some regions of the Earth suffer from water shortage? Setting aside man-made problems like water pollution, almost all the world's water is saline, or salty, and is often found in the oceans. Only about 2.5% is fresh water, and of that 2.5%, only a relatively small portion is actually available to sustain human, plant, and animal life. The rest of it is trapped in glaciers and ice caps. The question is, how can we produce more clean water? The solution is found in chemical engineering. Chemical engineers are responsible for designing environmentally friendly and cost-effective methods to not only cater for the growing needs of society, but to preserve the delicate ecosystems of our planet. One of the more recent methods that chemical engineers have designed to face the problem of water shortage is desalination. Our project was to design a desalination process. We did a series of calculations based on concepts such as thermodynamics, fluid mechanics, and mass balances. This enabled us to work out parameters and specifications for different components of the desalination plant. Fun stuff, right? Sit tight.
So you may be wondering, what is desalination? Desalination is simply the extraction of pure water from seawater, leaving the dissolved salt behind. As chemical engineers, our mission is to figure out the most effective way of carrying out an operation, taking into account factors like our desired output rate, cost, safety, and feasibility. For our project, we used different types of equipment. We used pumps. Pumps are used to move seawater from the ocean through the plant. A steam heat exchanger. These are used to heat up the seawater to the desired temperature. The steam in the first heat exchanger is used to heat up the seawater and will be generated using solar energy. A vaporizer connected to a vacuum pump. This is used to vaporize the seawater at a reduced pressure and therefore temperature, and separate the pure water vapor from the seawater. Condenser. To liquefy the pure water vapor that has been separated from the seawater in the vaporizer. Another heat exchanger. To reduce the temperature of the condensed water to 30 degrees using cooler seawater. And finally, a mixer. To mix the hot concentrated seawater from the vaporizer with fresh seawater at a lower temperature in order to cool it to below 30 degrees so it can be returned to the sea.
The design stage for any process involves developing schematic representations to show the basic components and layout in a way that is easy to understand and visualize. Once we had decided upon which components were needed, we used computer-aided design software, AutoCAD, to make a process flow diagram. Next, we calculated the heat duties for the heat exchangers, heater, vaporizer, condenser, and cooler, using a combination of mass and energy balances and information about the composition of the seawater as well as the temperature. We then used these heat duties and information provided about the heat transfer coefficients of each heat exchanger to determine their respective areas using this simple equation. Area equals heat duty over the heat transfer coefficient times the log mean temperature difference.
The final task in our design of the process was to choose a suitable pipe diameter for the pipes to be used in the process, and then calculate the pump duty of the pump that moves the seawater to the first heat exchanger, the heater. This was found using fluid mechanics principles. Using this equation, the suggested diameter of the pipe was 29.28 millimeters, but the closest commercially available size is 32 millimeters. Next, we used the volumetric flow rate and the total pressure drop in the pipe to calculate the work done by the pump, and given a pump efficiency of 80%, we were also able to calculate the pump duty of the pump. In summary, we were presented with a problem that affects people today, getting fresh water from seawater. Using engineering techniques, we were able to find the most suitable solution that will maximize the amount of clean water produced and minimize the cost of production and the effect on the environment. Hopefully you enjoyed learning about the process.
Bye!